In this segment, I want to introduce energy. And where we're headed in this chapter is towards one of my favorite ideas in all of physics, possibly my absolute favorite idea in all of physics, and that is the idea of conservation of energy, which says that energy can never be created or destroyed. But that's coming. First, we have to figure out what energy is, right? You've probably used that word. You certainly have. We drink energy drinks. If you're feeling lazy one day, you might say, gosh, I have no energy today. We talk about energy independence as a political issue. So what is energy? And it turns out that energy itself is very hard to define. In fact, if you look in our textbook, the first paragraph in the chapter about energy does not define energy. It says energy is hard to define, and it is. We're going to first understand different types of energy. So while energy itself writ large is difficult to define, individual types of energy, now those are much easier to define and very well defined. So what we're going to do is we're going to build up our understanding of energy as a big idea. We're going to build that up by understanding different types of energy. Kinetic energy is energy of motion, and we'll use K to represent that. This wrecking ball has more of something when it's moving than when it's at rest. What is that something? Well, energy. So kinetic energy is energy of motion. Potential energy is energy of position. So this roller coaster has more of something because it's at the top of the hill than it would have if it was at the bottom of the hill. What is that something? It's potential energy. It has more potential energy here than here, and it is its position that gives it that. This woman has a bow, and a bow also stores potential energy because this position here has less energy than that one right there. So that is potential energy. It is energy of position. Now be a little bit careful. A lot of times we see this word potential, and we want to think, ooh, something's about to happen, right? Potential in everyday language, it has this connotation of something's about to happen, right? A 5-year-old has a lot of potential. A 43-year-old, not so much, right? So, but that's not the way that the word is used here. In physics, potential energy means energy of position. That's it. In fact, you may have learned in another class that potential means the potential to move. That potential energy has the potential to move. It's true, but that's not why it's potential energy. It's potential energy because it's energy of position. And I guess the problem with that conception of it, that potential energy is energy of something that's about to happen is, well, so this ball has potential energy because it's on this box, right? Its position at the top of the box has more energy than if it were at the bottom of the box on my desk, right? So it has more energy up here than it would have down here. And does that give it the potential to move? Sure, if I give it a little nudge, boom, the ball falls off. But that's not the only way I can make it move, right? I could apply a force to make it move. Okay, sure, that's fine. We'll learn later that's called work. What else? Is it possible that kinetic energy of one object can make another object move? Let's see. I've got another ball. If I give it some kinetic energy, can it make the ball move? Yep, it sure can. So, my point is that potential energy is energy of position. And you may have learned, or you may have an idea in your head that potential energy means something's about to happen or it has the potential to move. It's just, yeah, that's true, but lots of types of energy can make things move. Here's a battery. A battery contains chemical energy which gets converted into electrical energy at the terminals. I can put this in a little toy car. Guess what it can do? Make the toy car move, right? So any kind of energy could make something else move. That's actually true. So we want to try and avoid the trap of thinking of potential energy means something's about to happen. It doesn't. Potential energy means energy of position. Other forms of energy include thermal energy. You may have, in another class, you may have learned about absolute zero. Remember that absolute zero is this temperature at which all molecular motion ceases. So every object has some thermal energy if it's not at absolute zero. And absolute zero is super cold. It's like negative 273 degrees Celsius, negative 500 something Fahrenheit. It is super duper cold. Any object that's not at absolute zero has some thermal energy. This ball has some thermal energy. An ice cube taken out of the freezer is very cold, but it has some thermal energy. So thermal energy is energy associated with temperature. We've also got chemical energy. If I put gas in my gas tank, I'm doing so for the chemical energy it contains. If I eat a sandwich, I'm doing it not only because it tastes delicious, but also because it contains energy, chemical energy, that I can use to teach a physics class or throw a baseball or whatever I want to do. Nuclear energy is another form of energy. The nucleus of an atom stores a tremendous amount of energy, and humans have devised various means of getting at that. Okay, so we've got all these different forms of energy, and we could probably add to this list if we really wanted to. There's different ways of sort of categorizing these things, but this is a good starting place. So we've got these different forms of energy, and we need to understand that the total energy of a system might include multiple types of energy, right? So even if our system is just simply this baseball, right, then we could say, hey, this baseball has a lot of different kinds of energy. It has some thermal energy because it is not at absolute zero. There is chemical energy stored in the bonds that are holding the atoms together, making the molecules that make this baseball, right? So it's got thermal energy, there's chemical energy, there is nuclear energy stored in the nuclei of the atoms that make up the molecules that make up the ball. Whew. It's sitting here on a box, so it's got potential energy. I could give it a little roll, and now it's got potential energy and kinetic energy, and all those others, right? So, in other words, the energy of a system, it doesn't just have one kind of energy or another kind of energy. The energy of the system is the total amount of energy that each part of the system has, and it's the total of all of the different types of energy. And so, we can just add it up here. Like we've done this in different places in this class. Now, energy is nice. One of the reasons why energy is nice is because it's not a vector. And so I often find that students feel like when we hit the energy chapter, a lot of times I feel like when we hit the energy chapter, students breathe a little bit of a sigh of relief because the ideas are still super interesting, but honestly the mathematics gets a little bit easier. And part of the reason why is that energy is not a vector, right? So we don't have to worry about any directions here. We just straight up add stuff up. That's how much energy we have. Okay. So one of the big ideas here is energy transformations. And energy, human, like I said in the beginning of this lecture, right? We use the word energy all the time, and humans consume a tremendous amount of energy, both in the form of food that we eat, but also in the gas that we drive in our cars and the lights that we use to see at night, and the electricity we use to plug in our computers, to power our computers so that we can record lectures, right? We use a ton of energy. But energy is only useful to us humans when we convert it from one form to another. So right now, I'm using energy to speak and conduct this lecture, right? And so what kind of energy? Well, my body runs on chemical energy. And so right now, my body is converting chemical energy into kinetic energy, sound energy, hello, some thermal energy, it's getting warm down here, right? So that chemical energy in my food, it's only useful to me when I convert it into another form. The chemical energy in your gas tank, in the gas that's in your gas tank, it's only useful for you when you run it through your engine and you convert it into kinetic energy going somewhere and potential energy going up a hill, right? So energy is super important to us humans, but it's only important to us when we change it from one form to another. It's an interesting and subtle point about energy. So we can then divide up the universe into the system and the environment, where the system is all of our collection of interacting objects, and the environment is everything else. And much like with the momentum chapter, when I say it like this super generally, it seems like, oh gosh, what does that mean? How do I know what the system is and what the environment is? But I think you'll find that when we start talking about specific problems, it's just not that bad. The system is just the stuff that's described in the problem. And we'll find that it's not as tricky as it might seem at this point. So, the system is our collection of interacting objects. Maybe it's me and the ball, for example, right? So, within the system, we can have all kinds of different transformations of energy. So energy can start out as kinetic energy and get transformed into potential energy, or from potential into chemical energy, or chemical into kinetic, and back and forth, right? So we can have all these energy transformations, and again, that's when it's useful to us humans. And again, kinetic energy, we use this K, it's energy of motion. Potential energy U, thermal energy E thermal. I already defined those terms. So the total energy here of the system is all of the different types of energy, but within the system, those types of energy can be transformed from one into another. So let's try and wrap our brain around some of those transformations, and we're starting our conversation very general here. So here are some different types of energy transformations. Here we see that this person has just lifted up a very heavy object from low to high. So what happened? That object gained potential energy. And if we say, well, it was at rest at the beginning, and now that person has lifted the object up and now it's at rest again, then the kind of energy it gained is potential energy, because it had no kinetic energy to begin with, no kinetic energy to end with, so it gained only potential energy. Where did that energy come from? From the athlete's breakfast, right? So we have chemical energy stored in the athlete's food, which they have now transformed into gravitational potential energy, energy of position. Here we see this baseball player sliding into a base. Well, what kind of energy did he have as he's headed into the base? Well, kinetic energy. But as he's going, he's slowing down. So he's losing kinetic energy. He was moving, he's slowing down, so he's losing kinetic energy. What's happening to that energy? Well, it's turning into thermal energy. The seat of his pants is a little bit warmer because of the friction between him and the ground. So here we see kinetic energy transformed into thermal energy. Here we see a campfire happening, right? This campfire is burning. And so what kind of energy is stored in that wood? Chemical energy is stored in the bonds between the atoms, in the molecules that make up the wood. When the wood burns, there are big long molecules inside the wood that are big carbon and hydrogen chains. And those carbon-hydrogen chains, they combine with oxygen from the air to produce carbon dioxide, carbon monoxide, and water vapor, and they release thermal energy. So here we see chemical energy stored in the bonds of those big long molecules getting converted into thermal energy. You know, there's also some light energy there and we could probably hear some popping and crackling, some sound energy, right? So there might be, you know, if we were to sum up all of the transformations that are happening in any process, it would probably be pretty complicated. And so we'll really want to, focus on sort of the big transformations that are happening here. Here we see this diver, and this diver right now, on this diving board, the diving board is very springy. So the spring, right? And so the diving board has stored some elastic spring energy, some position energy, some potential energy, because it is flexed. When that diving board releases, it will shoot the diver up. The diver will start moving, and he will have kinetic energy. As the diver rises in the air, that kinetic energy turns into gravitational potential energy. Of course, at the same time, this gentleman is converting his breakfast into thermal energy, right? And ultimately, all of this energy came from the chemical energy stored in his body. Here's an example. A skier is moving down a slope at a constant speed. What energy transformation is taking place? This is kind of a tricky one. Why don't you think about it on your own, and I'll see you on the other side. Okay, so here we see the skier going down the slope. Well, what's happening to their kinetic energy? Is it increasing, decreasing, or staying the same? Well, it says a constant speed. And since kinetic energy is energy of motion, I haven't given you an equation yet. We will, right? But kinetic energy is energy of motion. So we have the same object at the same speed. Is his kinetic energy changing? It's not. Therefore, we're not creating new kinetic energy. We're not losing kinetic energy. Therefore, we don't have an energy transformation involving kinetic energy here. What is changing? Well, is the skier's gravitational potential energy changing? It is. Their position is changing. They are going down the hill. Therefore, they are losing potential energy. So I think it's got to be gravitational potential energy to something. Well, so that means it's either B or D. And we already said he's not speeding up or slowing down, so it can't be D. It must be B. And indeed it is. The skier is losing gravitational potential energy. Where is it going? It's going into thermal energy. Friction between the skis and the skier is what's causing him to not speed up, right? Our discussion of forces up till now should make it so that you can see that if the skier is not speeding up as they're going downhill, there must be friction present, right? So that friction, guess what? It's causing the skis and the snow to be a little bit warmer. Therefore, what's happening here? Gravitational potential energy to thermal energy. Again, the really tricky one here is a lot of students are tempted by this one. But again, the kinetic energy is not changing. So that's why it's not D. Here's one. A child is on a playground swing, motionless at the highest point of his arc. As he swings back to the lowest point of motion, what energy transformation is taking place? Okay, so as the child is swinging back down, the child will be speeding up, right? So the child starts up high, and as the child gets lower, they lose gravitational potential energy because this position has more energy than this position. So the child loses gravitational potential energy, and the child is speeding up as that happens. So since the child is speeding up, gravitational potential energy to kinetic energy. How can we tell he's speeding up? Well, it says he's motionless, and then he swings back down to the lowest point. So he wasn't moving, and then he was moving. So we definitely gained some kinetic energy. Where did it come from? Gravitational potential energy.